All right, 637H, manganese ion, BiSO3. Is that the bismite? Manganese, bismite, permanganate, and bismuth. Mn+2. All right, so what we're doing here, again, we're balancing these equations. Identify the half reaction first. So just this part where the manganese is going to the permanganate ion. We have to be sure we include the charges, right? Balance everything but oxygen and hydrogen. It's balanced. Balance oxygen with water. 4 waters over here. Balance the hydrogens by adding protons to the side that needs the hydrogens. Oops, that's supposed to be 8 there because we have 8 hydrogens over here. Okay, so now we look at the more positive side. This is a positive 7, this is a positive 2, sum of a positive 7. 8 H pluses and 1 minus from the MnO4 minus. That's a net of positive 7. On the left here, 2 or 1 Mn+2, and that's it. So positive 7, positive 2. We need 5 electrons over here so that the positive 7 is equal to the positive 2 on the left. So there's the first half of the reaction. Bismuth, bismite ion to MnO4 minus ion. Going to just the bismuth ion. All right, so now we have, to balance oxygens, we need 3 waters and 6 H pluses to balance hydrogens. Okay, that's done. Electrons on the more positive side, this is a positive 5, this is a positive 3. Looks like we're going to need 2 electrons over here. Okay, looks pretty messy. When you see something really messy like this, you wonder, am I doing it right? This is balanced. 4 oxygens, 8 hydrogens, 8 hydrogens. 8 plus 1, that's 7 plus. This is a 2 plus. We need 5 electrons here to make it even. 6 H plus here, 6 H's, 1 bismuth, 3 oxygens, 3 oxygens. The charge here, 2 minuses, 6 pluses, that's 4 plus. Oh wait, that's not right. Oh yeah. Let's try that again. 2 minus, 3 minus, and 6 plus. That's 3 plus, so that's 3 plus. Well, if that's the case, then we're going to have to multiply this top one by 2 and the bottom one by 5, right, to find the least common multiple. So that the electrons are going to cancel out, and the water, well, we better just do it. It's going to be confusing. So let's write down the whole thing. We'll start up with the top here. 8 waters plus 2 manganese ions plus 2 plus 10 electrons plus 6 times 5 is 30 protons plus 5 bismite or bismite. I don't know if that's the bismite or the bismate. Going to 2 permanganate ions, 16 H plus ions, 10 electrons, 5 bismuth plus 3 ions, 15 water. All right, so down here at the very bottom, we'll write the final equation. We have to cross out our 10 electrons. We have 30 protons here, 16 here. So those 16 are going to be canceled out, and we're going to end up with just 14 protons on the left, 8 waters, and we're going to end up with 7 waters over here. So we have 2 Mn plus 2s plus 14 protons. plus 5 bismite or bismate ions, 2 permanganate ions, 1 bismate. Is that, how do I get, no, that's not right. This can't be just 1, it has to be 5, right? 5 here. Because we multiplied the 1 times the 5 here, so there's 5 of these bismuth ions. Okay, and then we end up with 7 waters. 637H, looks like a killer. 2 manganese, 14 protons. All right, we got it. All right, 637H. 637I, H3ASO3. Arsenous acid, dichromate, arsenic acid, and chromate. Can we already do this one? Plus 3 here. Okie dokie. So we need to balance this by, again, identifying the half reactions. ASO3 going to H3ASO4. Water on the left side here to get 1 more oxygen. Plus 2 protons on the right side to get that extra hydrogen. Maybe 2 more hydrogens, right? Arsenics are balanced. 2 electrons on the right side to balance that. Chromate ion, Cr2O72 minus, going to the dichromate ion, going to the chromium ion. All right, chromiums need to be balanced. Now we can balance our oxygen. Then we can balance our protons. Now we balance our electrons, plus 12 on the left, plus 3, 9 electrons on the left. Plus 14 plus minus 2 is where we had 12, plus 3 here, so 9. All right, so this thing is going to be multiplied by 9, and this thing is going to be multiplied by 2. That's, again, kind of a sticky, weird situation, so you might want to go back and double check. Net charge here is 0, net charge here is 0, net charge here is plus 14 minus 9, 10, 11, plus 3. Oh, no, that's the problem. We made a mistake here, right? Because we have 2 chromium plus 3 ions. So when we were looking at the charges to determine which is the more positive side, we said that this is a positive 12 on this side, but this is a positive 6 on this side, not just a positive 3, because we have 2 of those. All right, good. So I think we caught our mistake there. Positive 12, positive 6. We're going to need 6 electrons over here. And that means this one doesn't need to be multiplied by 9, it needs to be multiplied by 3. Okay, good. That makes sense. So, I mean, now it fits, it's right. The charges were not correct, but now they are. Plus 6 on this side, plus 14 minus 8. Minus 8, that gives us 10 minus that plus 6. Okay. All right, so write it all out. Start off with 3 waters here. Plus 3 H3ASO3. 6 electrons plus 14 protons plus Cr2O72 minus the dichromate ion. All right, yields 3H3AsO4 arsenic acid. 3 times 2, 6 H plus 6 electrons plus 2 chromium ions plus 7 waters. Okay, so 3 waters cancel out 3 of the waters over here, so this is going to be left with 4 waters. 6 electrons cancel out. There they are. Any protons on the left? 14 and 6. 6 cancel out there. It's this 14. It's going to go to 8. All right, so then we have this component, 8 protons, the dichromate ion, giving us 3 arsenic acids, 2 chromium ions, and 4 waters. All right, we can check out I there on that one. Okay, good. We got 639. Okay, so we're balancing the following equations for the following reactions occurring in basic solution. So basically the same thing, but we just add the last little step, which is basic solution. Okay? 639. 639A, CrO4 2 minus plus S2 minus S and CrO2 minus. All right, so we'll start off with S2 minus going to S. All we need to do is add 2 electrons, and that one's done. Then we'll do CrO4 2 minus going to CrO2. CrO4 2 minus going to CrO2 minus. Okay, and in this one here, we need 2 waters over here, 4 protons over here, all right, and we need electrons. We have 2 electrons over here that we need, right? Because this is a 4H plus, and this is a 2 minus, so this is a 2 plus on this side, and this is a 1 minus. Actually, we need 3 electrons, right? 3 electrons. Because this is a 4 plus and a 2 minus. 4 plus and a 2 minus, that's a plus 2. And this is a minus 1. So to get to there, we need 3 electrons. All right. So we need to multiply this top one by 3 and this bottom one by 2. All right. So that gives us 6 electrons plus 8 protons plus 2 CrO4 2 minuses, chromate ions, plus 3 S2 minuses yields 2 CrO2 minuses, 4 H2O, and 3 S's and 6 electrons. Okay, so we have 6 electrons on both sides. And we have 8 protons here. We're solving this for basic conditions again, like the problem instructions indicate. So we need to add 8 hydroxide ions for the 8 protons that we see, right? And that's going to make 8 water molecules. Okay? And 8 water molecules here, 4 water molecules here. That means these 4 water molecules are going to be gone, and this is going to be left with just 4 water molecules, right? Okay, and that should be it. Okay, so let's double check that one in the back. 639A. 2 chromates, 3 sulfurs, 4 waters, 2 CrO2 minuses, 3 sulfurs. Oh, we forgot the 8 OH minus ions. We added 8 OH minus ions over here. We also have to add 8 OH minus ions over there. All right, good. 639A. B. All right, so we have the permanganate ion, MnO4 minus plus C2O4 2 minus, the carboxylate ion, yielding carbon dioxide and manganese oxide. Is that correct? Okay, so we want to identify the half reactions. We'll start off with MnO4 minus going to manganese oxide. We need to make sure the manganese are balanced. They're balanced. We need to make sure the oxygens are balanced. We need 2 more oxygens over here, so we add 2 more waters to the right. Then we have to balance the hydrogens by adding 4 protons to the left. Now we have to balance electrons by adding 3 electrons to the left, because this is the more positive side, has net positive of +3 with the 4 pluses and the 1 minus. And this has no charge here, so we need to get it all the way down to neutral with 3 electrons. All right? The second half reaction, C2O4 2 minus going to carbon dioxide. All right? We need to make sure initially that everything but oxygen and hydrogen are balanced, so we need to make a 2 there for the carbon dioxide, so that the 2 carbons on each side. Now the oxygens are balanced already. Okay? So we don't need to balance the oxygens, we don't need to balance the protons, we just need to balance the electrons by adding 2 electrons to the right. That gives it the same charge as the one on the left. Right was a charge of 0 initially, left was a charge of -2. 0 is more positive, therefore we had 2 electrons there. All right, we multiply this by 3, we multiply this one by 2, because we need to have 6 electrons in both of them so they cancel out. We just knew that because 6 is a common denominator between the 3 for the 3 and the 2. All right, on the left side, we're going to have 6 electrons, 8 H pluses, 2 permanganate ions, 3 carboxylate ions. On the right side, we're going to have 2 manganese oxides, 4 waters, 6 carbon dioxide, and 6 electrons. All right? So we have 6 electrons on both sides of the equation. We can cancel that out right now. We can cancel out any waters if we had to or could, but there's only 4 waters over here. There's not 4 waters, or there's not any waters on the left. Protons, just protons on the left. Now, problem 639, again, we're balancing in basic solutions. So we have to look where there's H pluses, and it's usually it's just going to be on one side, right? Because otherwise they would have canceled out. And then we add 8, or the same number of hydroxide ions, and we have to add that to both sides. All right, now when we add 8 hydroxide ions to the left side here, this converts to 8 molecules of water. All right, so the result is 8 molecules of water on the left, and now we can cancel out these 4 molecules of water and change this to a 4. All right, so that should be what's in the back of the book there. All right, let's double check. 639, 4 molecules of water, 2 permanganates, 3 carboxylates, 6 carbon dioxides, 8 hydroxide ions, and then 2 manganese oxides. All right, good. All right, 639. 639C. So we'll do this one first, N2H4 going to NO. We need to get equal amount of nitrogens first. Then we have to add 2 water molecules to the left here. And then we have to balance protons by adding hydrogens. So N2H4 doesn't have a charge, right? NO doesn't have a charge, and chloride ion has 1 charge here, and chloride ion has 1 charge there. So nothing charged in here. So 2 water molecules. We have 4 hydrogens here. 2 times 2 is 4, plus 4. That's 8 H pluses. All right, and then we need 8 electrons. The more positive side. All right, ClO3 minus going to Cl. We need 3 waters over here. Okay. To give us 3 oxygens. Now we need 6 H pluses over here. And then we're going to need 6 electrons as well to get back to this -1 charge on the right side. All right, now we can see that we need to multiply these by something. 6 times 4 is 24. 8 times 3 is 24. So then we have 6 waters, 3 azides, N2H4, 24 electrons, 24 protons. I'm going to leave out the 24 electrons because we know we're going to have that many, and I'm going to leave out the 24 protons because we're going to have that many on this side as well. So then we have 4 ClO3 minuses. Then we have 6 NOs here. 8 times 3, we're going to leave those out. But like we said, we'll leave out these 2 because we know they're going to get crossed out. We can see that, right? 4 times chloride ions, 4 Cl minuses, and then 12 waters. Okay? So we have 6 waters over here, 12 waters over here, so this is going to be reduced to 6, and these are going to be gone. All right, let's see how we did. 639 C. 4 chlorates, 3 azides, 4 chlorines, 6 NOs, 6 waters. All right, 39 D. Nickel oxide, manganese hydroxide. Nickel oxide, O2, nickel 4 oxide, manganese 2 hydroxide. Going to manganese 3 oxide and nickel hydroxide, nickel 2 hydroxide. All right, so we'll look at the nickel oxide here first. Nickel hydroxide. Oxygens are balanced, we just need 4 protons over here. Correct? And then we're going to need 4 electrons over here. Oh no, not 2, not 4 protons, 2 protons. 2 protons. 2 H pluses, and then 2 electrons. Okay, the other one is the manganese hydroxide. Going to manganese 3 oxide. All right, we have 3 waters on the right and 3 oxygen. Oh, first we have 2 manganese here, so we need to have 2 to get that second manganese there. Now we have how many oxygens here? 2, 3, 4. 4 oxygens on the left and 3 on the right, so we need 1 water over here. Now we have 4 protons on the left, and we have 2 protons on the right, so we need plus 2 H pluses here, and then we're going to need 2 electrons there. All right, so it looks like electrons and protons, you can see, are going to cancel out. We'll be left with the nickel oxide, the 2 manganese 2 hydroxides on the left, and on the right, nickel hydroxide, manganese 3 oxide, and then 1 water molecule. Again, this is in basic conditions, but we don't have any protons left over, so we don't have to do anything, just like 637. 639, did we get it right? D, nickel hydroxide, manganese oxide, and water. Okay, got that one. 639E. Sulfite, permanganate, sulfate, manganese oxide. Okay, manganese 4 oxide, right? Okay, so go first with the SO3 minus 2 to the SO4 minus, or 2 minus 2. Okay, so what are we looking at? How many oxygens? 1 oxygen on the left is what we need, right? So we need to add 1 water to the left. Now we need to add 2 protons over here. All right, and that's going to make this the more positive side. It's neutral, so we're going to need 2 electrons to balance off to this more negative side. Is that right? 4 oxygens, 4 oxygens. 2 protons, 2 protons. All right, so that one looks like it's done. Now we go manganate ion, permanganate ion, to manganese oxide. We need 2 waters on the right. That's 4 protons on the left. And 3 electrons on the left, because we already have a negative charge here and 4 negatives here, so that's 3, and there's nothing over here. 3 electrons on the left. So this is going to be multiplied by 2. This top one is going to be multiplied by 3, correct? So that gives us 3 waters and 3 sulfites. So these 2 right here, right? Plus 6 electrons, I'll leave those out. 8 protons. It doesn't look like the protons are going to drop out completely, so I'll put them into this equation for a bit. 8 protons there, and 2 MnO4 permanganates. And we're going to get 3 sulfates. 6 hydrogens. I'll leave out the electrons. 3 manganese oxides, and 6. Oh, wait, I'll start over. Or that 3 manganese oxide is wrong. It's only 2 manganese oxide. But is this right? 6 H plus? Yeah. 2 manganese oxide. All right, because this manganese oxide is being multiplied by this 2 down here. And then 4 waters. This 2 is multiplied by that 2. Okay, so we see we have 8 protons here, 6 protons here, 4 waters here, 3 waters here. So I'll cancel out these 3 waters here with 3 of them over here, so we're left with 1 water right there. I'll cancel out these 6 protons and leave this with 2 protons. All right, now we're balancing this in basic conditions, so wherever there's protons, we have to add 2 hydroxide ions. And if we add it to the left side, we have to add it to the right side too. 2 hydroxide ions. All right, so these combine here to form 2 water molecules, 2 H2Os. I have one over here though already, so that is going to be dropped out, and this is just going to be 1 left over. All right, 3 sulfites, 1 water, 2 permanganate ions yields 3 sulfates, 2 manganese oxides, and 1 hydroxide ion. Do I only have to add 1 hydroxide ion? Wasn't this 2 hydroxide ions? Because I added 2 protons earlier, right? Or I had 2 protons left over on the left side. 8, yeah. 639. Okay, let's see how we did. 3 sulfites, 2 permanganates, 1 water, 3 sulfates, 2 permanganate or manganese oxides, and 2 hydroxide ions. All right, good. That's 639E. 641. Balance the equation for the 641. When a very dilute nitric acid reacts with a strong reducing agent such as magnesium, the nitrate ion is reduced to ammonium ion. Write a balanced net ionic equation for the reaction. Very dilute nitric acid That's NO3. Or sorry, HNO3, that's nitric acid. Magnesium reacts with magnesium. What does it form? Ammonium ion. NH4. No, ammonia. No, the ammonium ion. That's right, the ammonium ion. NH4, and that has to have a plus. The ammonium ion. Write a balanced net ionic equation for the reaction. All right, well, if this is going to this, then magnesium must be going to, this is being reduced, magnesium must be oxidized, Mg2+. Okay? So, how is this going to be working out, right? It says again, the nitrate ion is reduced to the ammonium ion. Now we can double check that that's an actual reduction, right? We can look at our oxidation state of nitrogen here. Oxygen's -2, that's a -6. Hydrogen's a +1. So +1 plus what equals -6, so it's a +5 here. Nitrogen's a +5. Here, hydrogen's a +1, there's 4 of them, +4. Nitrogen's only a -3, so it is a -3. So it goes from +5 all the way down to -3. All right, and that's due to the magnesium ion, which is going from 0 to +2. But obviously it's not balanced, right? So now we want to balance that. So we can look at HNO3 going to NH4, and we should be able to use the same rules. Nitrogens are the same here. We have 3 waters on the right because we needed 3 more oxygens. Now we have 4, I'll put a charge up here, forgot that charge. 10 protons on the right side, and we have 1 over here. So we have 9 H pluses over here are needed. And now this has a 9 plus on the left and a 1 plus on the right, so we're going to need 8 electrons to balance out these sides, right? And now the magnesium, Mg going to Mg +2. The only thing we have to do is have 2 electrons on the right. So now we're going to have to multiply this by 4 to get it to balance. And we're going to then have 9 H pluses plus HNO3 plus 4 magnesium, this part here. That's all on the left. On the right, NH4 plus 3 H2Os plus 4 magnesium ions, and then you get your 8 electrons, which we left out for 4. Okay? So this should be the balanced equation for what's occurring there. Anything else we can cancel out? All right, that's 641. Oh. Oh, okay. So in their equation, we have the same answer, but they have this HNO3 ionized, so that H went with that there. And that's fine. Either one of those is really okay. 3 waters on the right. Okay, great. So, 643. Laundry bleach, such as Clorox, is a dilute solution of sodium hypochlorite. Write a balanced net ionic equation for the reaction of sodium hypochlorite with sodium thiosulfate. The hypochlorite is reduced to the chloride ion, and the thiosulfate is reduced to the sulfate ion. So we can write out the molecular equation, or just the chemical equation first with the sodium ions, but the sodium ions aren't going to do anything in this reaction, and that's they remind us that by saying that the chloride, or the hypochlorite ion goes to chloride ion. All right, so we can just write the ions. We don't have to write the sodium ions as well. Just the anions here are doing anything. So we have OCl minus plus S2O3 2 minus going to Cl minus and SO4 2 minus, the sulfate minus, chloride ion and the sulfate ion, right? Okay, so let's start off with the OCl minus going to the Cl minus. We need a water over here, we need 2 protons over here, and we're going to need 2 electrons over here. This was 2 plus, 1 minus, so it's a 1 plus, and this is a 1 minus before we add the 2 electrons. So now they're balanced, okay? Again, we add electrons to the more positive side, and this was the more positive side with a +1 charge, and we add them until it equals the other side. All right, and the other one is S2O3 2 minus going to SO4 2 minus, okay? There's 2 sulfurs here, and let's see, 2 sulfurs, 2 sulfurs, right? We had to add a 2 to get 2 sulfurs on both sides. Now we need oxygens. 3 oxygens on the left for 8 oxygens on the right. 3 oxygens on the left. So we need 5 waters on the left. Now there's 5, 6, 7, 8, 4, 8. Now we need protons. We need 10 H pluses. Whoops. 10 H pluses on the right because we have 5 protons here. Or 10 protons here, so we need 10 protons there. Now we need electrons. The more positive side looks like this is a +6 because there's 2 times 2, that's a -4, and a +10, so that's a +6. This one is just a 2 minus. So we're going to need 4 electrons, no, 6, 7, 8 electrons. 8 electrons on the right, right? Correct? 8 electrons there. So that'll make this a -2 charge over here, like this one is a -2. So this is a -2, and now this should be a -4 plus 10 minus 8, which yields a -2, which is the same as this over here. All right, so we needed to add 8 electrons to the right. Okay, so we see that this needs to be multiplied by 4. Electrons are going to cancel out, but we're going to be left with, let's write this out first, 8 protons on the left, 4 hypochlorite ions on the left, 5 waters on the left, a thiosulfate on the left. On the right, we have 4 chloride ions, 4 waters, because of this 4 here, right? Put it over there to remind ourselves. So you can see it a little better. My head might get in the way. 4 water molecules, 2 sulfates, 4, 2 minus, 10 protons, and 8 electrons. But the 8 electrons we already didn't add because we knew they were going to drop out. Protons, how many protons drop out? Well, there's 8 over here and 10 over here. So these are going to be dropped out, and we're just going to be left with 2 over here, correct? Waters, 5 over here and 4 over here. So these 4 are going to be dropped out, and we're going to be left with just 1 water. Okay? And so that looks like will be the final. Let's make sure we got it. 643, 4, 1 water. No, let's see where we got it. 643. 1 water, 1 thiosulfate, 4 chlorines, 2 sulfates, and 2 protons. All right, that was 643, correct? Yeah. All right, 645. Ozone is a very powerful oxidizing agent, and in some places ozone is used to treat water to kill bacteria and make it safe to drink. One of the problems with the method of purifying water is that if there's any bromide ion in the water, it becomes oxidized to bromate ion, which has shown evidence for causing cancer in test animals. Assuming that ozone is reduced to water, write a balanced chemical equation for the reaction. All right, so we have ozone, O3, being reduced to water. All right, and we want to write a balanced chemical reaction for this. Okay, to use to treat water, kill bacteria, and make it safe to drink. One of the problems, okay, so ozone, assuming that ozone is reduced to water, write a balanced chemical reaction for the reaction. soon in a acidic reaction. Okay, so what they're talking about is not just this reaction, the reaction between the bromide going to the bromate. All right, what do we got here? O3 going to water. We need to have 3 oxygens on the right, so we need a total of 3 waters on the right. So that's going to need 6 H pluses here for ozone to be converted to bromate, and that's 6 electrons also to balance that charge. All right, that looks good. Bromine going to bromate, BrO3. 3 water molecules on the left. Oh, this is a BrO3 minus, though. All right, BrO3 minus. Very important. Whew. Good thing we remembered that. Okay, Br going to bromate, BrO3 minus. We have 3 waters, 3 oxygens, 6 protons, plus 6 protons. How many electrons do we need? Well, this is neutral over here. This is plus 5, so we need 5 electrons over here. Huh. Okay, is that right? That would have to be multiplied by 6, I guess, and 5 here. I'll put the 5 over here so you can see it better. All right, so that gives us 30 electrons and 30 protons. I'll write down the 30 protons because they're not going to cancel out. Or they're going to, well, we have a different number on the right here. So plus 5 ozones, plus 6 times 3, 18 waters, plus 6 bromines. Oh, let's see. Oh, no, this isn't bromine. This is a bromide ion. Sorry, I didn't read that problem very good. Bromide ion, so we got to step back a little bit. So we have the bromide ion going to the bromate. Okay, so now we need 3 waters, 6 protons, or 6 protons. 3 oxygens, 6 protons. Now this side is going to need 6 electrons. All right. So that facilitates our lives a little bit because the 6 electrons and the 6 protons are going to cancel out. And all we're going to have on the left is this, and all we're going to have on the right is this. And we have 3 waters as well canceling out. So ozone plus bromide ion goes to bromate. Is that it? 645. That's it. All right. Good thing we caught that. 647. Balanced molecular, ionic, and net ionic equations for the reactions of the following metals or balance them with the hydrochloric acid to give hydrogen plus the metal ions in solution. So manganese, hydrochloric acid, right? So manganese, Mn gives Mn plus 2. All right, so we have HCl if we want to. I'm going to get rid of that chloride ion. It's just going to be a spectator. So, and the product here is hydrogen gas. And you can look in your book and verify how these reactions occur, right? So for H plus to go to hydrogen gas, we have 2 hydrogens on the right. We need 1 more here. So we have 2 H pluses like that, and we're going to need 2 electrons here, correct? 2 electrons on the left. For the manganese, Mn going to Mn plus 2. We need 2 electrons there. So this is balanced now. We have 2 H pluses plus Mn yielding H2 and Mn plus 2. All right. Okay, what's next? Cadmium, giving cadmium plus 2. Well, we shouldn't have just erased that because we see 2 H pluses going to hydrogen gas with 2 electrons, and we see cadmium going to cadmium plus 2, giving off 2 electrons. So cadmium, 2 protons, yields cadmium ion and 1 hydrogen gas. Tin plus 2. Yeah, they're all going to be the same. I guess the only thing that we haven't been doing is we haven't been including the Cl minus here. All right, that would be the molecular equation right up there. Okay, good. 647, let's verify that we did those right. Yeah. Okay, 649. On the basis of the discussion in this chapter, suggest balanced chemical equations for the oxidation of metallic silver ion with dilute HNO3 and concentrated HNO3. All right, 649. Okay, so if we look for our dilute and our concentrated nitric acids, right? So oxidizing acids, which are our acids, sulfuric acid and nitric acid. Concentrated, so on page 229, we see our chart there. And based on this discussion, silver ion with dilute and concentrated. All right, so we're looking at for silver ion with dilute and concentrated. So there's dilute, concentrated, very dilute. So silver ion is very dilute with strong reducing agent. Silver ion is going to be reduced. It's not a strong reducing agent. Silver ion wants to be reduced to form silver metal. It's a strong oxidizing agent. So we're going to go with the dilute equation where we have NO3 minus plus 4 protons plus 3 electrons yielding NO gas and 2 waters. All right? So that is the half reaction for the dilute nitric acid. And then we have the silver ion, Ag plus, going to Ag, 0. So we need to balance this half reaction. We need an electron on the left there. Wait. Ag plus. Wait. On the basis of the discussion of this chapter, suggest balanced chemical equations for the oxidation of metallic silver, metallic silver to silver ion. So it's the other way around, Ag going to Ag plus, and giving us an electron, right? All right, so if this is going to happen, then we're going to have to multiply this by 3, correct, to get the electrons to cancel out. So we have NO3 minus plus 4 H pluses plus 3 silver ion atoms yielding NO plus 2 waters plus 3 electrons. Oh, the 3 electrons we left out, right? We have 2 waters, 4 protons. Okay, so let's see. Any other questions? All right, so we're here on 643, or sorry, 649, and we got our final net ionic equation. Now, if you look at this here, then you're going to see that in the end, we have some silver ions that are by themselves. So if you wanted to go from the net ionic equation to the molecular equation at this point, you would need to include the counter ion here, some nitrate ions, some more NO3 minus. You need 3 more. So you would have to have 4 NO3s here, and then an additional NO3, or 3 NO3s here. Let's see, did I do that right? Yeah, yeah. 3 additional on this side and 1 more on there. And these could come together to form silver nitrate. So that's what they did in the back of the book. But otherwise, I wouldn't expect you to do that, and I think that's kind of hokey, because it's a little bit of difficult comprehension just to understand the problem, let alone take it all the way back to that molecular ionic equation. All right, so for the concentrated HNO3, we look at our chart again and remember what concentrated nitric acid does on 229, page 229. Concentrated nitric acid, NO3, 2H plus. So we have NO3 plus 2H plus an electron going to NO2 and water. And again, this is silver metal going to silver ion, Ag plus. So this one here, we need to add that electron again. And then we're going to have to multiply this by 2. All right, so this is in concentrated nitric acid. And what we're going to get is NO3 plus our 2 protons plus our electron there. Oh no, we don't have to multiply this by 2 because it's just 1 electron up top and 1 electron on the bottom. All right, so 1 electron here plus the silver atom yields NO2 plus water plus the silver ion, and the electrons cancel out, electron here. So electrons cancel out, all right. Protons, so this would be the final, but again, in the back of the book, they probably are going to, this is NO3 minus, sorry. In the back of the book, they're probably going to identify that we need 1 more NO3, so we'll make this 2, and we call this Ag plus, or AgNO3. Okay, so that's probably what they have in the back of the book. All right, that's 49B. Silver solid, 2 HNO3s, and they have these together also in the molecular equation. Silver nitrate, 1 water, and a nitrogen dioxide. All right, good. 649. Got that one.